Well, hello, everybody. My name is Richard Everheart, and I work for a company called AAD. You probably haven't heard of us, but if you've been to a major international airport, particularly in the United States, you've probably seen our work. We're a digital signage company primarily for airports, but also other places. And that's all to say we are incredibly interested in display fidelity, which means we have to have a sophisticated understanding and capability when it comes to modifying color space. And that's what I'm here to talk to you about today, is color. This talk is intended to be a broad overview of the challenges you're likely to face when introducing color awareness to a Vulkan application. It is not intended to be a detailed mathematical exposition, nor am I going to go into detail about what I think your implementation ought to look like. That being said, we will be covering XYZ color space, what a color volume is, and how to transform them. And then I'm also going to go over our approach that we use to get advanced color processing and HDR working across signage, which culminated in a solution for getting HDR and color processing working on X11 and Wayland in Linux without driver modification and without actually modifying X11 or Wayland compositors. So I'm going to start with a brief lesson on physiology. The human eye has a retina, and in your retina are cones. There are three types of cones for red, green, and blue wavelengths of light. Unlike a lot of cells that have a neurological function, cone cells are not actually emitting an all or nothing activation response. They are what's called tonically active, which means they are basically emitting analog signal data. This analog data is a convolution of wavelength and brightness data, and it's believed that our occipital lobe has a bunch of complex neurocircuitry for making sense of this. However, the human brain is a stupid organ. It couldn't even come up with a cool name for itself. And as a result, it is by no means perfect at this. Certain waveforms of light that are different might actually look the same, and certain waveforms of light that are the same might actually look slightly different. It is the goal of a color space to find a rigorous mathematical equation for relating perceived color phenomenon to observed color phenomenon, or observed color phenomenon to physical color phenomenon. This is a big task. Nonetheless, if we were to define a color space today, we would probably define it based off of human physiology itself. And indeed, there is one such color space that does this. It's called the LMS color space, that is literally just defined by your cone activation functions. However, when we were developing this standard in the 1930s, these spectral sensitivities were not known, and as a result, they had to be supplemented with experimental data. If you're curious about what this experimental data looked like, the experiments consisted of two boxes with eye holes in them. The box on the left had three lamps that emitted light at constant wavelength, but variable brightness, and the box on the right had a single lamp of constant wavelength and constant brightness. The goal of a participant in the experiment was to selectively modify the brightness of the lamps on the left such that they blended together to match the color perceived on the right. This experiment essentially measured the additive properties of color. They measured how color primaries could be added together to form unique colors. And from this experimental data, color matching functions were fitted that were used to define something called CIE 1931 color space. You'll commonly see this represented in the two-dimension as a visual aid, but it's just a projection to the RG plane. And this visual aid lets it clearly be seen that the color space encompasses all the values in the triangle CRCGCB. However, there's a small problem with this color space in that the red color component is actually not strictly additive, it's subtractive at certain wavelengths. And as a result, your color matching functions were actually negative in certain respects, which resulted in a really oblique color space for RGB. There was concern that this would mess up calculations because computers didn't exist yet. And so the solution was to map your CMFs to a strictly positive domain. In doing so, you derive something called CIE XYZ color space with a few convenience tweaks like making the luminance component on its dedicated, Y value. You'll commonly see this used in context to normalization, in which it is CIE lowercase xyz color space. You'll also once again commonly see this visualized as a projection onto the XZ plane, in which this is called CIE xy color space. And if we introduce the Y vector component again, we get CIE XYY color space. Obviously, this terminology is incredibly ambiguous, but just know whenever we are dealing with the mathematics of color, we are pretty much invariably looking at XYZ lowercase color space. So in the modern sense, a color space is defined in context to lowercase xyz color space, and it simply includes color primaries that form a sub-triangle in the unit triangle of xyz color space and a white point. This is the chromaticity diagram for sRGB, if anyone cares. Speaking of white point, a white point is just the maximum color in your color space. You'll normally see it defined in terms of units Kelvin. Rest assured, your monitor is not actually 6,500 Kelvin. The reason it's defined this way is because it's defined in context of the color of an incandescent black body when heated. Unfortunately, color spaces are lacking in a key area. They do not specify how luminosity ought to be interpreted. A color volume remedies this by augmenting a color space with a function for mapping luminosity called an EOTF, or electric optic transfer function. The inverse of this is either given as inverse EOTF or optic electric transfer function. And as I said, it simply is a map of luminosity. Their color volume can be linear or nonlinear, and data passed through a color volume can likewise be linear or nonlinear. And this pretty much specifies whether the data was interpreted using a linear or nonlinear EOTF. A linear color volume is required for certain calculations, namely changing color primaries, also for white point conversion, and then surprisingly, you need it for texture filtering and alpha blending as well. Luckily, it's really easy to make nonlinear content linear. We simply apply the inverse ETF to it, and this is commonly called linearizing or de-gammaing your color volume. There's also this notion of dynamic range in color volumes, which is simply the ratio of min and max luminance, or I should say max and min luminance. HDR, or high dynamic range, allows for up to 10,000 nits of max luminance, whereas LDR only allows for 100. HDR attempts to make use of this higher allowed luminance using a much different EOTF than LDR. And namely, it uses something called the perceptual quantizer EOTF. Which is exceptional, but you'll commonly also see hybrid log gamma used, which is not nearly as exceptional. This is used out of convenience. Unfortunately, the vast majority of HDR applications out there today use hybrid log gamma. And if you've ever seen HDR and you haven't been blown away by it, it's probably because it's using HLG and not PQ like it should. So I want to drive home that LDR and HDR is just 100% incompatible with each other. And this should be visible to anybody simply by viewing these graphs of the EOTFs. A value of 230 for our EOTF used in our recommendation 709, which is the standard LDR color volume, will be about 75% of the brightness of your monitor, but the same value in PQ will be 33% of the brightness of your monitor. So this is a massive difference. And if you attempt to render HDR content as LDR and vice versa, you should expect a surplus of banding on all these other terrible image artifacts. These are examples of color volume. These are their EOTFs. I only gave this slide because a lot of people, if you've ever wondered what sRGB actually looks like under the hood, this is it. So how you convert color volumes is actually pretty simple until you get to tone mapping. You have to linearize your color space, then you end up changing the primaries and white point before delinearizing again. And then depending on whether you're going from lower dynamic range to higher dynamic range or vice versa, you either inverse tone map or tone map respectively. If your dynamic range is the same, you don't have to do any tone mapping. However, you might have to account for what's called the display model in the case of HDR to HDR. So changing the color primaries is pretty simple. It just amounts to generating what's called a color transformation matrix. This is effectively finding a matrix that sorts color space to XYZ color space, and likewise for sync. And then our CTM is just the source matrix times the inverse of the sync. To find this source matrix, you effectively just find the individual contributions of each component on your X, Y, and Z vectors. You then scale your white point separately and use this scaled white point to generate your conversion matrix. Similarly, white point conversion is also pretty simple. It amounts to generating a chromatic adaptation matrix. However, instead of going through XYZ color space, we're going to assume we're already in XYZ color space, and we're actually going to go through LMS color space to do this. So it amounts to converting your white points for your source and destination to LMS color space using a XYZ to LMS conversion matrix, and then you simply scale your white points in LMS color space and then convert them back to XYZ color space. So this is all fairly simple, right? Unfortunately, tone mapping is not that simple. For those of you that are unfamiliar with image processing, tone can be thought of as the gradient of luminosity. It's effectively the first derivative of your image's luminance. And a tone map is a transformation of higher dynamic luminosity gradient to lower dynamic luminosity. The mathematics aficionados in the crowd should no doubt recognize this as Poisson's equation, which is the standard equation for remedying divergence in vector fields. This is ideally the mathematical way you would use to tone map. Unfortunately, we commonly don't have detailed destination gradient information, and also likewise we won't be able to have we won't be able to basically get a second Laplacian to adequately describe the divergence between our gradients. And then this is more complicated by the fact that the human brain just loves to make things up too. So a good tone mapping algorithm will naturally account for all of this. And there is a standard for tone mapping called ICAM06. If you are doing tone mapping, please, for the love of God, use ICAM06. You can do it easier using histogram equalization, sigmoid matching, all of these stereotypical data processing techniques, but ICAM06 is by far the best by a mile. Tone mapping naturally requires you accounting for discrepancies between your mastering and target display. Your mastering display is the display that the content is intended to be rendered to, that it was created for, and your target display is essentially the content it's actually going to be rendered to. The information you need to account for this is included in a metadata specification called SMPTE 2084. It includes a lot of just like min and max values, but really what's important are your mastering display color volume metadata and then your max CLL and max FALL metadata. So the display model is basically a way where you convert the brightness range of one display to another. And I say brightness range in the sense of min and max luminance, not necessarily the luminosity gradient. That's different. So to do this, you essentially just use this equation and you take into account the max CLL that is provided by your HDR metadata. There are methods that make use of max frame average light level here, but this one does not. You might use max FALL though in other tone mapping algorithms other than ICAM06. If you are going from, say, if you're going from lower brightness to higher brightness, you use a forward display model. This is like pretty much not necessary though, because you only really account for the display model in going from HDR to LDR. And LDR displays are so low fidelity that they don't differ meaningfully. So this step really is not necessary in the vast majority of cases. As I said, ICAM06 is the standard for doing this. This is ICAM06. The idea is it goes through what's called a bilateral filter to split your image into a base layer and detail layer. It only tone maps the base layer such that details of your image are preserved. This looks complicated, and from a theoretical point of view, it is very complicated. But from an implementation point of view, it actually is surprisingly easy to implement. Much like everything in computer graphics, it boils down to matrix multiplication. So tone mapping is already pretty complicated, and then inverse tone mapping is really complicated. An inverse tone map transforms lower dynamic gradient information to high dynamic gradient information, and it's complicated because it requires generating and inferring new information. It essentially requires upsampling image luminosity gradient. Obviously, AI methodologies are really good at upsampling things, and they excel here, although they're not necessarily performant, and you can't use them in real time for something like a game engine, although this is improving. There are real-time methods for this, but that are performant, but they aren't nearly as effective. I could spend 2 hours talking about inverse tone mapping, and unfortunately, we don't have that time. You guys are all probably interested in how you actually deal with color volumes in Vulkan, however. So I'm considering a use case where you have some image with some source color volume that you want to render in a Vulkan renderer that is using some intrinsic disparate color volume. In order to do this, there are a few things you have to be cognizant of. First and foremost, you need your source image to be linear. If your image is not linear, your GPU might apply a gamma operation or D-gamma operation to your buffer, which will corrupt your color volume. Secondly, now you've told Vulkan that it's linear. And as a result, Vulkan will try to blend it as if it's a linear color space, which will also corrupt your color volume. So if you want to do this correctly, you have to implement blending yourself in shader, and likewise for filtering. This isn't hard, but it is very annoying. So this is just an overview of what the methodology would look like in Vulkan. The only thing I really want to say here is that unless you are rendering directly to the display, you will not have control over your sync color volume. It will essentially be what your swap chain image color space is. And also, you would never really use your EOTFs directly. You would only use them as 1D LUTs. If you are a direct renderer, though, you have a lot more freedom, but also a lot more challenges to solve. Namely, you have to relay to the physical display how it should process your more colorful data. And there's an idea here that because you are already talking to the display and the device driver naturally talks to the display, you should do all of your color volume conversion in the driver. The alternative would be to offload all of the rich, complex mathematics of color to every direct renderer application. I think there is a third option here, and it's to add a intermediary layer that I call a just-in-time post-processor layer. The idea here is to, by all means, leverage driver features if they are available, but if they are not available, then we have a software fallback, which basically intercepts the buffer that is going to scan out, imports it into Vulkan, does color processing in Vulkan, and then sends it back to scan out. If you've ever written a zero-copy video player, it's the same idea here. It's just we're applying zero copy to the scan out buffer. So again, this is the methodology. We take our DMA buff, which represents the scan-out buffer contents, and we import it into a compute shader in Vulkan. We then change its color space to the color space of our post processor, do tone mapping and inverse tone mapping as required, beautify it if we really want to, and then change it to our display color imagery. Obviously, we're importing the DMA buff into Vulkan directly, so our input and output does not have to be a DMA buff. It can be something like a VK image, in which case the methodology is effectively the same. We use the extension external memory DMA buff for Vulkan to do this. I really think there needs to be a Berbeki Ben symbol or a here there be dragons warning on the main page for this extension, because it really requires a proficient knowledge of how DMA buffs work in Linux to use effectively. And unfortunately, there are some meaningful implementation discrepancies here. That being said, we are not a allocator, we are a post processor, so we have to respect the format of the buffer that we're changing the colors of. So this means we have to respect the DRM format modifier, which if you've ever worked in driver development, you know is kind of a hassle in and of itself. Luckily, we do get a boon here in that the format modifier that is optimal for scanout is usually optimal for compute as well. And this is especially true in the case of NVIDIA that I've realized. And then, as I said, we use a compute shader to do this simply because using like a ping pong renderer or the fragment shader is not efficient enough. And we prefer to use storage buffers as opposed to storage images because I found storage images with DRM format modifiers are pretty bugged. And finally, at this point, our scene has already had all of its like nice lighting effects baked in. So there's an argument, do we really need the alpha channel at this point? And we'd rather work in a higher bit depth to ensure that our PQ EOTF has the maximum, bits it needs to work with. On the DRM KMS side of things, since we are talking to the display, we have to tell the driver what info frames to send to the display. And the bare minimum info frames you have to send to do this basically talk about your D gamma, gamma, and CTM information. This is the bare minimum. Your display, if you only send these, will not know it's an HDR. Which may or may not cause problems depending on your exact display. I personally have not encountered any issues with it, and I have a spectrometer and can guarantee this is using PQ color space when you do this, but your mileage could very well vary. There are driver-specific DRM mode object properties you can use to tell your monitor in the HDR, but as I said, they're driver-specific. i915 does not have any, which is annoying. And then the last thing I want to say is when you are importing and exporting Vulkan buffers for use in scanout with DRM and KMS, you have to be really careful your sizing information is relayed correctly. If it is not, you theoretically can get overflow on the GPU when going to scanout, which has a bunch of fun undefined behavior that I've dealt with. So in our approach, we actually integrated this into a meta implementation of libdrm. For those that don't know, libdrm is the standard user space library for mode setting in Linux. And this effectively augments libdrm with post-processing capabilities. which effectively augments every application that uses libdrm in Linux with advanced color processing capabilities. So X11 and Wayland compositors basically get free HDR support by linking to my meta implementation of libdrm without actually having to do anything themselves. And then we went the Wayland route and used a Unix domain socket for advanced configuration if you care about that. So we now have a case where if you're an HDR application, you want to render it on Linux, you can actually use our post processor on your Vulkan buffer directly to tone map it to LDR with the expectation that our window manager that's using our meta implementation of libdrm will now later inverse tone map it properly to HDR. Alternatively, if you're confident in your HDR implementation, you can request our post processor to render it to a dedicated hardware plane and it will respect your color volume. So this is actually surprisingly efficient after optimization. I'm not going to claim it's like efficient on the battery. I've targeted less than 1 millisecond to do all of my color post processing, including intercepting the DMA buff, etc., and it's performant. And so it's effectively a performance solution for taking LDR content and inverse tone mapping it as HDR, which is really nice. So this is the game No Man's Sky, which is a very colorful game in its own right. And No Man's Sky does have HDR support technically, but it breaks from release cycle to release cycle, and I'm pretty sure it's using hybrid log gamma. So what we can do is then intercept the buffer that No Man's Sky, or that your, I guess, window manager is sending to scan out, and we can do inverse tone mapping on it. And this brings out a rich vibrancy of color that is just simply not experienced in the base game. I will say this image has been inverse tone mapped and then tone mapped back to iCam 06 because I had no idea what the presentation setup at this conference was going to be. So it looks even substantially better on on my mastering display. And then finally, we can do the same thing with just the window manager output itself. This is my daily driven X11 window manager running Emacs, and neither of those applications are color aware at all, and yet I'm using my post processor to make it look like it was natively rendered as HDR. So in conclusion, color is really complicated. Vulkan unfortunately doesn't support importing images with PQ color space, although it does technically support presenting them. The thing, though, that's really depressing is color just is not in a good state. And if you're going to use something that's unforgiving like perceptual quantizer color space, you have to have lossless abstractions every step of the way. If, say, your image loader does not handle color correctly, then even though your renderer handles it correctly, it's just not going to look correct. So unfortunately, I think the best thing you can do right now is probably just to implement an inverse tone map as a post-processing effect. I hate to say it, but there's just so much complication. Someone's going to get it wrong either before or after you, so you might as well do the easiest thing. And obviously, if you want to go all out and do it post-processing directly before scan-out, you get plenty of other perks. And anyway, that concludes the presentation. If you have any questions, yeah, by all means.
This is not a question. This is just the most sincere and heartfelt comment I could possibly say from the bottom of my heart. I'm so glad that there's people like you thinking out this shit so that I
Oh, thank you.
On behalf of everyone, thank you.
Thank you.
So from the presentation, it wasn't exactly clear to me why you couldn't rely on hardware blending and the other features that you mentioned. Is this because the data isn't actually linear, and so if you use like hardware blending, it's going to be treated as linear, or is there something else going on?
That's correct. So when you use hardware blending, it should treat it based on the in accordance of the Vulkan format of your image. So if it's linear, it's going to blend it in accordance with like linear color volume. This is why you like have to specify sRGB because this is meaningful information you're telling the driver to use. So Vulkan does not support like PQ pixel format, or I'm sorry, color volume format. So it has no way of like applying the correct EOTF. So unfortunately, you then have to tell it linear and then supplement that EOTF yourself in shader.
Okay, thank you. I have one more comment. You said there's no user space API for synchronization of DMA buffs. I think it was Faith. We worked on an API like 2 years ago for importing and exporting fences.
So I tried to use that, and this might have been, I was working with a NVIDIA system when I encountered this bug, which probably is meaningfully different, but I tried to use that synchronization API and it did nothing for me.
Yeah, it's not going to work on the NVIDIA proprietary drivers.
Oh, yeah.
Anything that is in upstream Linux, though, should work fine. You can just import and export your sync files. Like, that's how Vulkan Windows System integration works today.
Okay.
It's how a bunch of compositors are working. The API is solid and it works. It's just that, yeah, implicit sync on the NVIDIA proprietary stack just doesn't work.
Okay, so that was just see because I was targeting NVIDIA because I wanted this to work with game media and they're kind of the most common use case. So okay, that makes sense.
Yeah,
I didn't have the problem in Intel, you're right, and this cropped up only after I switched to
Yeah,
NVIDIA.
and you shouldn't have it on AMD or any of the others. It's literally just
Yeah, it was
the
literally
proprietary
it was.
stack.
I had other problems on AMD, but this was purely an NVIDIA thing. Thanks for clarifying that.
Thanks for your presentation. It's very informative. And I have small comments on the OETF and EOTF that are, according to the Khronos data format specification, the OETF and EOTF is not necessarily inverse
yeah.
function, right?
Yeah.
Yeah, that's a small comment on that.
Yeah, it's and I thank you for bringing that up. Yeah, I think Hugo said something about lying at certain points. For the sake of time, I lied at certain points in this presentation for the sake of time, and that is a caveat I left out, but you're 100% right. And you primarily see like OETF used in context to like digital imaging devices. And there is, if you're not careful, the meaningful differences there will cause problems. So thanks for bringing that up.
Thank you.
So,
Oh no, this guy.
okay, so we've got EOTFs, EOTFs as well. So I can get my source image, I can get it into a linear color space to do my lighting calculations. Then I can get it into LMS for tone mapping, and then I can get it back out to whatever the display wants, etc. But that one thing about that linear color space that I should be doing my lighting calculations, and what should that be?
That then becomes purely up to your implementation. I just work with displays. I am not really in my knowledge is not on like rendering complex scenes. So I mean you can theoretically calculate all your lighting effects in PQ color space, and that I guess would work if you really want to handle that. But again, I can't really give much advice on that.
Okay, I think that's it. Yeah, so thank our speaker once more time.
Thank you.